Okay, so we're going to talk about one-dimensional motion, and as we've been doing already, the real point here is not just like memorize some stuff and learn some equations, but to be able to do stuff. There's two sets of skills we're going to work on today. These are the conceptual skills. So if we're talking about an object or anything, we ought to be able to figure out where it's located in one-dimensional space, which is not super tricky, but there's a couple little twists to the plot, okay? More difficult is finding an object's displacement, which I'll define for you, but you have a general intuitive understanding that has something to do with how far something has moved. Average velocity, which again I'll define. You have a decent intuitive understanding of that already. It has to do with like how fast something is going. And average acceleration, which almost certainly your intuitive understanding is wrong. Whatever you think acceleration is, there's about a 75 to 80% chance that you're not right, because we don't use the term acceleration correctly outside of a physics class. So when we talk about acceleration outside of here, we don't use it in the same way. Over any period of time. And this is really open-ended because there's a billion ways to do this. And what I want you to be able to do is use all of those ways. It's not an algorithm where I say, okay, if an object has this position at one time and this position at a later time, subtract these two things and that's the displacement. That happens to be true, but that's not the only way you can find displacement. You can find displacement from a position versus time graph. You can find displacement from a velocity versus time graph. You've all done that before. You can find displacement by using equations that look like they're completely unrelated to any of the stuff that we're talking about. And we're going to look at all of those things. And you can look at, for example, you could find displacement ultimately by looking at the amount of force being applied to an object and its change in speed. You could figure out how far it's moved by knowing how hard someone is pushing on something and what its resulting change in speed is. That seems kind of crazy. Like, how do you find displacement from that? And the answer is, well, we've got like a bunch of stuff that we can work with. So ultimately, what we really want to be able to do is recognize that there's not just one way to find displacement. If I say, here's some scenario, here's some information, find displacement, many of you could find it one way, and many of you could maybe find it a completely different way. And those are all potentially valid ways of finding an object's displacement. And then when we talk about instantaneous velocity and acceleration, this is where the conceptual piece gets really weird, because this term instantaneous means no time goes by at all. But when we talk about velocity and acceleration, you'll see that those have to do with changes in an object's position, which has to take time, or changes in an object's velocity, which also has to take time. How far can something move in no time at all? It can't. I mean, if no time goes by, then it can't move. So if it can't move, then how can it have a velocity? And those are weird ideas and weird concepts that end up being super useful, even though there's a piece that's kind of out of grasp for us to understand. All right, so those are the things, the big skills we're going to talk about with this, and then when I show you Tracker in a little bit, we've got a set of skills for that as well. So we're going to start with the simplest possible scenario in which there can be motion, and that's the scenario in which motion is constrained along a one-dimensional line. So one-dimensional motion is motion in a straight line. All we know is that it's completely linear. It's not curved, it's not two-dimensional, which would be a plane. It's not three-dimensional, which would be like a cube or a sphere. It is one way in one direction, or the other way in the exact opposite direction. Those are our only options. A lot of times, we know something about the motion of that object. A lot of times we know, for example, that it is horizontal. If I roll something on the floor, then we know, well, it's not going up and down at all. Or if I'm up on a building and I drop something, then I know that it's moving vertically. So sometimes we know, Other times, we don't. Like I might say, hey, I had a piece of string in between my bedroom and the living room, and it was in a perfectly straight line. You know that's one-dimensional, but you don't know anything else. My bedroom might be on a second floor, and my living room might be on the first floor, so it might be at an angle, or it might be, completely horizontal, but we don't know what direction it is. Like, we don't know if it's north or south or east or west, so we can have these conceptual ideas as well. When we think about these one-dimensional motions in a straight line, we generally give that straight line a letter to indicate its axis. And if we have a line that's sort of horizontal-ish, or we know for sure that it's horizontal, or we just don't know anything at all, then we call it X. And if we know that it's vertical or really close to vertical, then we will call it Y. And so most of the time we just use X, because much of the time we don't know like what the linear orientation in space is, we just know it's a straight line. The only time we really use Y is when we are sure that it's either vertical or just so close to vertical that it's basically vertical motion, okay? And then we have positive and negative values for like stuff. We have positive and negative values for position and velocity, and it turns out acceleration as well. All of those are associated with the direction, and this is somewhat arbitrary. Our positive direction is going to be one direction, and our negative direction is going to be the other direction. Okay, and now what's going to happen is a little unknown, because it turns out this isn't working quite right, so my apologies if this ends up being a big fat mess, and this is just going to take a couple seconds for me to fix, but we'll just have to see. Ready? Oh, it worked. Okay, good. All right, so if we know we're moving in one-dimensional space, then we can establish that position is going to be somewhere along our one-dimensional line. And basically what we do is we just think of that one-dimensional line as divided up into even chunks. And in this class, most of the time those chunks are going to be measured in meters. We might use centimeters. We could use feet or inches or miles or whatever, but it's always going to be some unit of distance. And so if we know where something is, like if I know that a block of wood is located right here, then all I need to do is just give this spot a number. But what's that number going to be? Well, it turns out it is utterly arbitrary. What this number is depends on where we've decided 0 is going to be. Where is 0? It can be anywhere. If I tell you something is moving one-dimensionally, and I tell you that it's like 5 meters from where it started, that doesn't mean it started at 0 and ended at position 5. It could have started at 5 and ended at position 0. That's still 5 meters apart. Could have started at position negative 2.5 and ended at position positive 2.5. That's still 5 meters. Our position 0 is arbitrary. Sometimes the tools we're using tell us position 0, like the sensor was already set up so that the sensor itself was position 0. But some of you may have noticed you could actually change that. You could adjust the sensor so that it was positioned. You could have made the sensor itself position negative 31.8. And then everything would have been measured relative to that point. Position is a relative measurement. And our directions are also entirely relative. We can pick one direction and then the other direction's the other way. Again, sometimes our measurement instruments will have that built in. The sensor had a built-in positive direction. As you moved farther from the sensor, your positions became more positive. As you moved closer to the sensor, your positions became more negative. So that had a built-in positive and negative direction, but that could be changed as well. So there are adjustments that we can make to the instruments. Sometimes The zero and or the directions will be determined by the problem itself. If I give you a problem where I say an object starts at position 0 and moves to position 4, then you know its starting point is position 0 and it was moving in the positive direction. But if I just say an object moves 4 meters, where is it? You cannot say it's at position 4 or -4, or you just can't say that. You have to say, well, I'm going to say position 0 is right here. And now I can tell you where it ends up. It might be at position 4, it might be at position 3212.6. So in general, every time we deal with motion, whether we're dealing with one or more dimensions, we need to know where is position 0, which is arbitrary, and which direction is the positive direction. If this is position 0, then 1, 2, 3, 4, 5 meters, if we're supposing these are meters, in the negative direction is located right here. My positive direction is to the left, my negative direction is going to be to the right. This is 5 meters away from 0. As soon as you tell me where 0 is and what direction positive is, then I can give every location a number. And all those distances are relative, right? So we know 0 and -5 are 5 meters apart. And that would be the same even if we had placed 0 somewhere else. It's always going to be 5 meters apart. All right, so that's position. And then we are going to give a formal definition to something that you've been using for a while, which is displacement. So displacement is more than just how far something goes. Displacement has to do with the distance between an object's starting point and an ending point over some period of time, and the direction. Displacement has a definition. The definition of displacement is final position minus initial position for any period of time. And the terminology that we're going to use for displacement is delta x. That'll be for horizontal-ish or completely unknown directions. If we know something's moving vertically, then this becomes delta y, this becomes yf, this becomes yi. If we start working in 3 dimensions, but we will, when we start working in 3 dimensions, then there may be a delta z as well. Z is going to be our 3rd dimension. Things can move along a plane or in 3-dimensional space. For now, we'll just stick to 1 dimension now. This is final position, this is initial position. One of the things that you will find right off the bat is that there is no universally accepted way to write this. In some textbooks and online, this will be how it looks. Sometimes it looks like this. And this means current position, current being no subscript, minus initial position. This meaning your location at time 0. There is a million ways that we can have notation for this. You're going to see them all. And so one of the things that you're going to have to do is get used to it. I'm going to standardize my notation, and we'll do this not Thursday, I think, but next week. We'll do this according to the AP variables. So we're going to use the AP standard notation, but that's different from the book. And that's different from what you're going to see online, and that's different from the notation that I used 30 years ago. So there's no one accepted standard. Really, you just got to be able to use them all. Okay. So this is our definition of displacement, and displacement is what's called a vector quantity. The direction matters. And since we're using positive and negative to indicate our directions, then that's incredibly handy, because that means that if we just use our positives and negatives, our displacement will either be positive or negative. If it's positive, we know we moved in the positive direction on our axis. If it's negative, we moved in the negative direction on our axis. Mathematically, using positive and negative as our directions is much easier than using, say, left and right or up and down. Okay? It's way easier because the math will tell us the direction. And I mentioned that I want you all to be able to find displacement in a variety of ways. Here's an example of that. Given two locations, you ought to now be able to find displacement. If I tell you an object starts at position 1.6 and ends at position -3, you ought to be able to do that math to figure out what its displacement was as it moved from 1.6 to -3. You can also find displacement from a position versus time graph super easily. This should look familiar to all of you. This was our position versus time graph for the Motion Match lab. We can figure out where something is at any time because the coordinates of these points tell us time along the x-axis, comma, position along the y-axis. So for example, this coordinate was 3 seconds, comma, +2 meters. This coordinate was 5 seconds, comma, +1 meters. There's my final position, there's my initial position. What was my displacement? My displacement over that time period has to be -1 meter. You can also find displacement from a velocity versus time graph. That's trickier, but you did that as well. Your velocity versus time graphs looked like, like this. And we can find displacement by finding the area. If you find the area of this particular shape, you should have found that that was -1 meter as well. That's gonna be the base, which is 2 seconds, times the height, which turns out to be -1 meter, divided by 2 because it's a triangular shape. We can find displacement this way, or just by using this formula. So that's 3 ways that we can find displacement right off the bat. And then we have been using the terms displacement and distance sort of interchangeably so far, and that's okay for what we've done in the past, but now we need to deal with the fact that they're not the same. And there's 2 big things that we have to think about. One is, distance has no direction associated with it. If I travel a distance of 1 mile, I travel a distance of 1 mile no matter what direction I'm going. The other, more complicated difference is that distance is the total length of the path that an object takes. So if an object starts here, and then it moves like this, then the distance traveled is the total length of this curved line. Its displacement is the length of this line along with that direction, which, since this is 2-dimensional, there would be an angle associated with this. Those of you who remember your Cartesian angles, this looks like it's about -20 degrees or something like that on a standard Cartesian coordinate plane. So this means your displacement and your distance aren't always the same. They will be the same if you're moving 1-dimensionally in one direction. Then your distance and displacement will always be mathematically the same. Yeah?
So if an object like moves like back and forth like over and over again, and it does the like, could it have like a distance of like a mile, but the displacement is like nothing?
Exactly, yes.
Okay.
And in fact, that's exactly what happens when you run track. And so and this isn't, I'm not making like hilarious physics jokes here. If you start and end in the same spot on a track, then your displacement is 0. The difference between your starting and ending point is 0 meters. So you have no displacement. Now, we know you moved. I'm not saying like you didn't do any work to get there, but your linear displacement actually is 0 mathematically. And that's important because the equations that we're gonna develop tell us linear displacement. So we might end up with displacements of 0 for objects that moved really far. If I travel 10 miles this way and then 10 miles back, my equations should tell me that my displacement was 0, and they will. So that is a valuable distinction. We have to be able to understand that, okay? And distance and displacement are related to each other in much the same way as speed and velocity. So let's look at velocity. Velocity is talking about how fast something is going, but it also includes the direction. And just like there's a mathematical definition for displacement, there's a mathematical definition for velocity. And actually, it's average velocity that we're gonna look at first. Average velocity is displacement divided by the amount of time over which that displacement occurred. So this is the displacement of an object. It's gonna be a vector quantity. It's gonna tell us the distance between the object's starting location and its ending location, along with the direction of motion. And this is change in time. And this calculation will give us a rate, and that rate is called average velocity. That rate tells us, on average, how much an object's displacement changed per each unit of time. Okay? And so just like with just like with distance and displacement, this can get weird if an object is kind of moving back and forth or moving in a circle. Because when we think about speed, what we want to know is how fast is something going. And as something speeds up and slows down, as long as it's moving the whole time, it's like speed wasn't zero. But with velocity, you could potentially have a displacement of zero. So velocity has a direction and is related to displacement, not distance. Speed has no direction, and speed relates to distance rather than displacement. A lot of times we'll use those terms interchangeably, and you'll see why in just a second. But a lot of times we can use those interchangeably, but don't make the assumption that they're always interchangeable. If we go back to the example on the track, mathematically, if you run around the track once, your average velocity was zero. And that's not just fancy physics fun jokes. That is absolutely mathematically true. Every single equation that involves those two displacements, talking about linear motion, will tell you your displacement was zero, that means your velocity was zero as well. And that seems weird, and actually we can deal with it in physics because we have a completely different set of equations that we use for objects that are moving in circular paths. That's how we deal with it. We have a completely different set of equations for which that displacement wouldn't be zero. Okay? But if we're looking at linear displacement, which is like 1 or 2 or 3-dimensional motion, then an object that starts and ends in the same position has a displacement and a velocity of zero, no matter how fast it was going during that time, and that's weird. Your speed is different because your speed relates to the distance of the path and the direction doesn't matter. Here's where things get kind of interesting, is where we start talking about average versus instantaneous velocity. This is average velocity, okay? All you need to know to find average velocity is where was something at one time, where was it at some later time, and how much time went by. That's it. That will tell you the average velocity. If you want to know how fast something is going at any given moment, you need something a little bit fancier than that. So Laura, this is what you saw earlier. If you want to know how fast something is going at a given moment, you either have to use calculus, directly or indirectly, or you have to make an estimation. I'll show you how to do that in just a second. The calculus way of doing it is to recognize that if I want to know an object's instantaneous velocity, I'm making this same calculation as the amount of time that goes by gets closer and closer to 0 seconds. Instantaneous velocity tells us how fast something is going as it travels for exactly 1 nothingness of a second. No time at all goes by, yet it is moving. At that instant of time that lasts for exactly no time at all, how fast was it going? This fast. Mathematically, we can do this with calculus. Visually, it's easier to think about it graphically. Remember I told you that slope on a position versus time graph is velocity. Okay, so here's our old familiar position versus time graph again. If I want to know the velocity at any time, I'm going to find the slope. What's the slope right here? Well, it's 0. What's the slope right here? You figured out the slope right there was positive 1 meter per second. What's the slope right here? It's 0 again. The instantaneous velocity at all these points is equal to the slope of those line segments. Here, it's a little trickier because the slope here is changing. It starts off at 0, and as we talked about, it ends with a velocity of -1 meters per second. So how do you find the instantaneous velocity at any one of these points? You use the tangent. And what the tangent does is essentially take our time period and make it smaller and smaller and smaller. So I'm gonna kind of zoom in on this right here and just show you what that would look like. So if this is my curve, and I think about the whole time period, if I were to draw a straight line showing the average slope between this initial and this final position over this time period of 2 seconds. That didn't work. That's still not working. Anyway, that's the time period. That line would look like this. Okay? We can figure out the slope of that line. Change in y-axis divided by change in x-axis. This, by the way, would be -1. This would be 2 for that motion match graph, which means the average slope over that whole time period was -1/2 meters per second. But what if we picked a smaller time period? What if we looked at this time period right here, from here to say here? Well, now the line that connects those is closer to the curve. It's like it's not pushed out as far from the curve. It's closer to the actual slope of that curve. A curve has a whole bunch of slopes, but overall it's kind of closer to this as my times get closer and closer together. When you get to the point where your times are so close that you're essentially looking at a single point on the curve, then effectively what you're looking at is a straight line that touches the curve at that point and nowhere else. This is called the tangent, and mathematically it's equivalent to this. The slope at a point is equal to the rise over the run as the run gets so small that it's basically 0. You can estimate the slope of this line. Now, if I gave every single one of you a curve on a piece of paper and said, find the slope at this point, you would all find a slightly different slope because you would all draw a slightly different tangent line. And that's fine, it would be an estimate, and that's fine. But when we start using math to do it, we're all gonna get the same numbers. Mathematically, we can predict exactly what the velocity of this object would be at, say, 4 seconds, or at 3.2 seconds, or at 4.7 seconds. Mathematically, we can predict it because we know some other stuff about the way that this particular object was moving in the lab, right? So that is that's our velocity definitions. And velocity is weird. It's weird and it gets weirder. The instantaneous part is weird. The fact that it's related to displacement and not distance is weird. You're gonna get weird numbers that seem counterintuitive because we can have things that go somewhere and then come back. And as they start coming back, their displacement decreases. And as their displacement decreases, their average velocity will decrease as well. And that seems very counterintuitive to us. The last thing that we're going to talk about before I give you a tracker demonstration is acceleration. And this is the one where things really fall apart, because for most of us, we are very confused about the difference between acceleration and velocity. And I'll talk a little bit more about that on Thursday. I'm going to just kind of go through this today, and then there's one last thing to tease out on Thursday. But basically, acceleration is a rate. Acceleration does not tell you how fast you're going. It doesn't tell you where you are. It doesn't tell you how long you've been moving or how long you will move. The only thing acceleration tells you is how quickly your velocity is changing, okay? It tells you how quickly your velocity is changing. And it turns out that our formula, our definition of acceleration, is really similar to our definition for velocity. For one, we're really defining average acceleration. Average acceleration is equal to change in velocity divided by change in time. So if you know how fast something is going and how fast it's going at some later time, if you subtract the initial from the final velocity and divide by the amount of time, you'll get a number that tells you the rate of change of velocity. Since velocity has a direction, just like displacement, acceleration has a direction as well. And here's where things start getting weird. What do you think negative acceleration is? Right? What? Go ahead and say it.
A negative rate of change of velocity.
What does that mean? What would that look like?
Velocity going down.
Slowing down, right?
Well, no, like a decrease in your
Isn't that slowing down?
Well, I guess it would translate to slowing down eventually, but
Yeah.
in some way.
What do you think?
Like accelerating in the negative direction.
It's accelerating in the negative direction, but is that speeding up or slowing down?
Speeding up.
Speeding up? All right, so now we've got two people, both of whom are like sharp, that have two completely different opinions. And my opinion is even a different one. My opinion is we don't know. It could be slowing down or it could be speeding up. You don't know. And that's where it gets weird. The intuition is most people want to say negative velocity is slowing down, or sorry, negative acceleration is slowing down. Positive acceleration is speeding up. That's not always true. The next place people go is exactly where you went, which is really insightful, which is, wait a second, if you're going faster and faster in the negative direction, then you're speeding up and you have a negative acceleration. Which is true, but that's not always how it plays out. Yeah?
Isn't it, if you're speeding up, the acceleration sign and the velocity sign are the same, and for opposite, it's slowing down?
That's exactly right, yeah. So if you start with a negative velocity, then a negative acceleration will be speeding up, and a positive acceleration will be slowing down. If you start with a positive velocity, then a negative acceleration will be slowing down, positive acceleration will be speeding up. We'll look at all this stuff over the next several days. But for some of you, clearly, mathematically and conceptually, that makes some sense. For many of you, if you're one of the many, many people in here right now who's thinking, what now? Don't worry. That is perfectly normal at this time. Like that is where I would expect you to be, okay? So this is average acceleration. If an object is accelerating, objects can have an acceleration of 0, in which case the velocity is not changing over time. So that's fine. If an object has an acceleration with a non-zero magnitude, then that must mean the velocity is changing. And there's 3 ways that velocity can change visibly. One is an object can speed up, it can go faster. Okay? That can happen in the positive or the negative direction, whichever those are. Another is the object can slow down. And the third way, which we're not going to deal with really right now a lot, but I want to plant the seed for thinking about this, is objects can accelerate simply by changing direction. And this is where it's a little weird because many people are like, well, yeah, because if you, like a lot of times when I give these examples and then I say an object can accelerate by changing direction, a lot of times what people will say is, well, yeah, because like if you're going around a curve, you have to slow down. But that's not what I mean. Okay. If you're moving one-dimensionally, you absolutely have to slow down to change direction. If I'm going this way, before I can go this way, I first have to slow down and then I can start going the other direction. You have to. But if I'm moving in a circular path, I do not need to change my speed to go a different direction. I can walk at a perfectly uniform rate and change my direction at the same time. I don't have to slow down to turn. Okay? If you're in a car, sometimes it's smart to do that because you don't want to lose control. But even in a car, you don't have to slow down. If you're going 3 miles per hour, you can keep that speedometer locked at 3 miles per hour while you turn the steering wheel. As you turn that steering wheel, you're accelerating, simply because you're changing direction. Okay, and then the last thing that I want to talk about relates acceleration, average acceleration, to instantaneous acceleration. It's the same basic idea as instantaneous velocity, which is that if we start thinking about the rate of change of velocity as the amount of time over which that change occurs gets closer and closer to zero, then we're talking about instantaneous acceleration. How quickly an object's velocity is changing as no time goes by at all. At an instant in time, we know its velocity is changing, no time goes by, but if time were to go by, this is how much its velocity would change per second. We have a way of determining this graphically as well. When we were looking at motion graphs, I mentioned that there was something about the slope of a velocity versus time graph. And in my conversations with you, many of us talked about that, but this is the first time that I've told everybody that on a velocity versus time graph, the slope is acceleration. Just like on a position versus time graph, the slope is velocity. We saw this with our velocity versus time graph with the motion match, right? Should have looked something like that. The slope of these lines tell you the acceleration. The slope of this line is 0, no acceleration, constant velocity. The slope of this line is 0, no acceleration, constant velocity. The slope of this line is 0, constant velocity. This line, if you did the math, you would have seen that it had a slope of about -1/2, not just about, exactly -1/2. The units for acceleration, which we'll talk about next week, are meters per second squared. This means that every second, your velocity became 1/2 meter per second more negative. Okay, so after 1 second, you would have been traveling at -1/2 meter per second. After 2 seconds, you were traveling at -1 meter per second. And if you have a curve in the in the velocity graph, you can do the same thing, coming up with a tangent line and finding the slope of that tangent line. We're not going to deal with that. We're only going to be dealing primarily with constant acceleration. So this is about as complicated as it's going to get. Here's where it's weird. For the first part of the motion match, you're standing still. The second part, you're moving at a constant velocity of 1 meter per second, no acceleration. For the third part, you're standing still again. But if you never have any acceleration, then how could you possibly be moving? And the answer is, you were accelerating. If you had been able to do this exactly as it was described, which no one could, then you would have had incredibly rapid positive acceleration right at 1 second, and you would have had incredibly rapid negative acceleration right at 2 seconds. Some time had to go by here. This would have been a very large positive number during which your speed changed from 0 to 1 meter per second. And then there would have been another really large acceleration here, huge slope here, during which your speed went from 1 meter per second to not moving at all. So the slope of these lines are those accelerations that didn't last very long, very large accelerations that had a very short duration. All right, that's going to be what we talk about